Hello class, I just wanted to go over practice problem 8.1.4 for you. I've posted this Mathematica notebook to the discussion board for Unit 8. And I personally really like friction and this whole unit. I think it's a pretty interesting and fun concept to get to work with. So practice problem 8.1.4 asks us to find the angle at which this block will start to slide down the ramp. And you could imagine any number of kind of simple situations that are in real life that are analogous to this. But anyway, it gives us the weight of the block, which obviously is going straight down, and mu, which is the friction factor between whatever this ramp or plane is and the block, the surface of the block. And that in real life varies depending on a lot of different things, especially what the two materials are. Do you have dry rubber on dry rubber that's going to have a huge friction factor, or do you have wet steel on ice, which is going to have a really teeny friction factor? So in this case, point 4, that's probably something like wood on metal or wood on wood or something like that. A pretty normal kind of friction factor. So let's start over here. We're given this diagram and we are given the weight. We'll update this for this version of the problem, so it's actually 250, and I'll hit Shift Enter to get it to recalculate that. And then the friction factor obviously has changed from the last time I did this, so let's do Shift Enter and get the friction factor to update. This is kind of fun. If you're interested in seeing what different friction factors are for different materials and situations, you can check out that Wikipedia page. The first step when we do find when we want to get the solution, for this problem, is setting up a really good free body diagram, because this helps us to really understand what's going on. It's tempting, I know, with this kind of a problem to just say, oh, I know how to do this because it looks fairly simple, and it is. But if you take the time to really draw the free body diagram and think about what's going on, it'll pay off, I promise. So if we have a free body diagram like this, and we have friction obviously is a force that's pushing up against the sliding motion of the box, is what I'll call it, and then we have the weight of the box that's coming straight down. Those are the two obvious forces that are working, but what we have to do to make this make more sense, I think, at least this is the way I have to think about it, is I change my reference of thinking from x being horizontal this way and y being vertical this way to, we always called it x prime and y prime when I was in statics. So if we have x prime along this plane and the same parallel to this plane and y perpendicular to it, then that's going to make things easier down the road for us. Also, we need to break up our weight force into a normal force, something that's perpendicular to the plane, and what I'm calling the F slide force. So the force due to the weight, the component of it that is parallel to the plane that the block is sliding on and is opposed directly to friction. So if you think about that for just a second, you can imagine that if we sum our forces in the x prime direction along the plane, that when F slide becomes bigger than the friction force, that's when motion is going to happen. Over here they use the term impending motion. So impending motion, sorry, highlight just impending here. Impending motion means it's about to happen. So it means that the forces are equal to 0 at that point. So F slide is going to equal friction at that point. That's kind of our key little formula, is when does F slide equal friction? At that point, the box is going to start to move down the ramp. And so that will tell us then, at what angle. Imagine that this is on a hinge. Imagine that this is a hinge and we've got a handle over here, and we can raise and lower that ramp, and we're just trying to figure out at what angle, how high do I have to tilt this to get that box to start moving down the ramp. So that might be what we're trying to figure out, or that's just one way you can think of it. So if we, again, remember that we want friction to equal F slide, That's our sum of the forces in the x prime, that's what this little tick mark is x prime. Sum of the forces in the x prime direction equals 0, that's impending motion when it's equal to 0, is equal to friction minus F slide, because the positive x direction is going up the ramp. So friction in this case is technically positive, F slide is technically negative. You could set it up differently if you want to, whatever. So then that makes sense in English, but now we have to translate it into math language. So if we have friction minus F slide, well, what's friction? We know that friction is the fun equation. It's equal to mu times n. Mu is our handy-dandy friction factor, which in real life depends on a bunch of different things, and also the normal force. Now the normal force, if you remember, we talked about up here, that's also a component of the weight. So a lot depends on the weight of whatever this object is. So we also know theta is here, but theta is also here between the normal and the weight. So that's an important thing to remember, is this angle right here between weight and normal. So friction is mu times n, and n is the cosine of that angle times weight. So that's just the basic kind of trig we've been doing all semester. And then the sliding force, what's the sliding force? Well, that's even easier than friction. It's just the sine, or the opposite, of theta times weight. So now we've got this, we can set these up as variables. We can say Fn, or force in the normal direction, is equal to cosine of theta, and we have to put in degrees so that Mathematica knows we're talking about degrees and not radians, and multiplied by W, the weight that we set up here. And then if we say that friction is equal to mu times Fn, the normal force, then we've got our friction part all worked out. And then if we say that the sliding force is equal to what we talked about up here, sine of theta in degrees times the weight, then I can tell it to solve. I type in solve, make sure it's capitalized, square bracket, 0, remember your double equal sign, friction minus F slide, and I'm solving for theta. And then I hit Shift Enter, and it'll give me, I don't know if I updated these up here. I need to make sure I hit Shift Enter on all those, and then I'll just go through and hit Shift Enter on everything so that okay, look. It gives us two different answers for theta. It says theta could be negative 158, or it could be positive 21.8. Looking at our diagram, it's pretty easy to tell we want a positive angle, not a crazy negative angle. So we'll go with the 21. Let's type it in and see what we get. 21.8014. I'll type them all in because it's easy. And I'll hit grade, and voila, we got it. So that's how you do practice problem 8.1.4. Let me know if you have any questions or anything in the comments in the discussion board, and we'll take it from there. Thanks.